Welcome to lecture 13. This is on the priority ceiling protocol. So recall from lectures 11 and 12 that the reason for this protocol, which we will be calling PCP, is to rectify and also improve upon the two protocols that we have seen earlier, which were PIP, Priority Inheritance Protocol, and HLP, which was the highest locker protocol. So we want to improve the issues with both. So recall that with priority inheritance protocol, we had a lot of issues, chain blocking, unbounded priority inversion, deadlocks, and so on. And so basically with HLP, many of those things went away. But still the problem of inheritance related inversions was there because HLP in a sense boosts the priority of a process to a very high level, an unacceptably high level. So a low level process, just because it is holding a resource, its priority becomes very high. And as a result, many intermediate tasks, they actually start missing their deadlines. So we want to pretty much get the best of all worlds. So we want to somehow combine these two, PIP and HLP. So like in HLP, each resource is assigned a ceiling priority, where the idea is the same. You take all the tasks which may possibly request for a resource, which is assumed to be known accurately a priori, and the maximum of those is the ceiling priority of the resource, where we are assuming FIFO scheduling. Furthermore, what we do is that in this case we define something called a system wide ceiling, which is nothing but it is the highest of all ceilings for all the resources that are currently in use. So every resource, in a certain sense, if the resource is a hardware resource, it is protected with a software semaphore. So in that sense, a resource and a software semaphore will be used in the same context to mean the same thing. And each of these that are in use will have a ceiling, which is the maximum of the priorities of all processes that may in principle or potentially access the resource. So the highest of all of these, right? So if you have multiple resources that are currently in use, the highest ceiling of all of these, right, is the system wide ceiling or the current system ceiling. But note that unlike the definition of a ceiling, which is a theoretical maximum, this actually takes into account the resources that are currently in use. So in a sense, this is dynamic. So furthermore, what we do is that PIP is an improvement over PIP as well. So recall that this was a greedy approach. So if a resource is free, then promptly, even for that matter, HLP was also a greedy approach, which basically meant if a resource is free, it is given that resource. Okay. And so the idea was that you never hang on to or you never deliberately delay a request when the resource is free. But in this case, this is not a greedy approach. So here some degree of delay or some degree of deferral is there where we can purposefully delay a request and not give it the resource. So we will see this gives us some good properties, right, of deliberately delaying a request. So this will actually help us prove many things, and in practice, it's not that bad. So the main idea of PCP is the current system ceiling or CSC, which is basically the maximum of the ceiling of all the resources where these resources are currently in use. That's the most important thing over here, that the resources have to be currently in use, right? So at the time of the system initialization or system start, no resource is in use. That's the reason the CSC is initialized to 0, right? And gradually it increases and decreases, and again when no resources are in use, the CSC is 0. So there are two rules that regulate the protocol. The first is the resource request rule, and the second is the resource release rule. So the resource request rule goes like this, that the resource request rule again has two sub rules, but we'll look at this. So it has the resource grant clause and the inheritance clause. So let us look at the resource grant clause. The resource grant clause, which is a sub rule of the resource request rule, is basically applied when a task requests a resource. So, when a task is interested in a resource, when it actually requests for it, this is when this rule is applied. And the inheritance clause is applied when a task is made to wait for a resource. So, when you actually wait for a resource, so what happens to you and what happens to the holder of the resource, that is determined by the inheritance clause. All right. So, we look at two aspects. One is getting a resource granted, and the second is not getting it granted but waiting on the resource holder. So, these two are a part of the resource request rule. So, let's now look at the first clause of the resource request rule, which is the resource grant clause. So, the idea is that unless a task holds a resource that set the current system ceiling, so if the system ceiling has some value, so it's clearly the maximum of the ceilings of the individual resources. So if a task holds a resource that set the current system ceiling, so unless this is the case, it is not allowed to lock a resource, right? And right. So this is the first part of the sentence. We'll again take a look at the second part of the sentence, but the key idea is that if the current task in a certain sense is holding a resource that actually set the current system ceiling to whatever value it currently is, it is not allowed to lock a resource unless, of course, its priority is greater than CSC. So let me now make this slightly concrete, and I'll maybe give you 5 seconds for you to just read it on your own before I start speaking once again. So the thing is, let's assume that the system ceiling was 9. Then a task comes and it locks a resource which made the system ceiling 10. So given the fact that the task in this case, right, the task that set the ceiling 10, it holds a resource whose ceiling is 10. If that is the case, it is now allowed to lock resources. Any other task which has not set the current system ceiling to 10 is not allowed to lock a resource unless its priority is greater than CSC, which means that if its priority is greater than the current system ceiling, which is 15, right? So if its priority is 15, it will not only execute, but it will also fall in this unless clause, which basically means that it is allowed to lock a resource. All right. So basically, the point is that its priority better be very high, which is higher than the current system ceiling. Then, of course, it's a very high priority process. We personally have nothing to complain. Or the other thing is that otherwise, let the current task continue. So, if we actually think about it, if we look at this protocol, so what we will basically see that the system ceiling is actually the most important variable out here. And furthermore, if I have set the system ceiling to a certain value, then it means that for any other task to actually come and lock a resource, it needs to have a very high priority, which will be much greater than my priority. So, in that sense, I pretty much get more or less a blank sheet, a carte blanche, to lock as many resources as I can. So, we will look at this issue in great detail in the subsequent slides. But the key point here is that it is this clause over here that I simply cannot lock a resource unless my priority is greater than the system ceiling. Of course, this is assuming that I am not the one to have set the current system ceiling in the first place. So once we have seen this, so let's go slightly deeper. So assume a task Ti requests a resource Cr. So if it's already holding a resource, right, which set the system ceiling to what? So its ceiling priority equals CSC. It is granted access to the critical resource Cr. Otherwise, Ti is not granted unless the priority of Ti is greater than the system ceiling, which is exactly what we were discussing. So let us look at this again. If Ti is granted access to the resource Crj, so what does this mean? Right? So what this means is that either the priority of Ti is equal to the current system ceiling. Fair enough. So or the priority of Ti is greater than the current system ceiling, which is the other clause. So in any case, when Ti is getting access to Crj, if it is the first condition, right, then what we know is that the ceiling of Crj, right, the ceiling of Crj by definition will be greater than equal to priority of Ti, which in this case, as you can see, priority of Ti is equal to CSC. So basically, it will be greater than equal to the current system ceiling, right? So this is the first case. The second case is that since Ti is getting access to this, so this will be the same idea, that the same relationship will still hold, that the ceiling of Crj will be greater than equal to the priority of Ti, which is greater than the current system ceiling. So if you look at this in both the cases, what we will have is that the ceiling of Crj, all right, will be greater than equal to the current system ceiling. So what we do is we set the value of CSC to the ceiling of CRJ. So let me now clear the writing on this slide. So let us now look at the inheritance clause. So assume a task is prevented from locking a resource. So if it's prevented from locking a resource, the task that is holding the resource will inherit the priority of the block task, right? Of course, subject to the fact that the priority of the task holding the resource is lower than that of the block task. So in this case, what we will see is that there will be different kinds of blocking, including one kind of blocking which we have not seen before, which is because of this deferral, but we have not reached that point yet. But assume a low priority task is holding on to a resource and then a high priority task comes. It will essentially wait on the low priority task. So here also we will have something quite similar to priority inheritance, not the HLP kind. So recall that in the HLP protocol, the priority of TL was becoming the ceiling of the resource R. But in this case, that will not happen. In this case, the low priority task, right, which is currently holding the resource, will inherit the priority of the high priority task, which is quite similar to what we were doing in PIP, right, with the priority inheritance protocol. So we have now seen both the rules. We have seen the the request granting clause and the inheritance clause. So let us now look at the resource release rule, which is quite similar to the resource release rules of prior protocols. So assume a task Ti releases a critical resource CRG that it was holding. So the point is that what is the level of the current system ceiling CSC with respect to the ceiling of CRG? So right, so if the ceiling of CRJ is equal to CSC, then it means that there is a need to reduce CSC. All right, fine, fair enough. So basically here the idea is that there is a need to reduce CSC. So CSC can be reduced just by computing it from scratch, which is we take a look at all the resources that are currently being used. We take their ceilings, and the ceiling is a static attribute of a resource. So we simply take all their ceilings and we compute their maximum, and that becomes the current CSC. Otherwise, CSC remains unchanged. Furthermore, the priority of task Ti may also have been increased because of inheritance. So essentially, it reverts back to its original priority if it's not holding any resource, right, after releasing the current resource. Otherwise, it reverts to having the highest priority of all the tasks, waiting for any resource which TI is still holding. So what happens is that if TI is holding a bunch of resources, so what will happen is that let those resources be called R1 to Rk. There will of course be other tasks which are waiting on R1, other tasks which are waiting on R2, R3, R4, and other tasks which are waiting on Rk. So we take all the tasks which are waiting on these resources, we compute their maximum priority. That is the priority that task Ti will inherit, which of course could be, if task Ti happens to be the highest priority out of all of these tasks, it will not inherit anything. But even if there is one task which is waiting on some resource that Ti holds at this point of time, then it will inherit its priority. So the priority of Ti also needs to be updated using this rule. All right. So pretty much, we have to do our cleaning or our bookkeeping. Where what we do is that we simply remove the record of TI holding CRG by updating both the CSC if there is a need and the priority of TI, in the sense reverting it back to what it should be without CRG, again if there is a need. So let us give an example. Let's say in this case, higher the number, higher the priority. So the ceiling of R in this case is the maximum of 10, 2, and 5, which is equal to 10. And let us now assume that we have another task. Sorry, we have another task T4, which has a priority of 8. So the issue that will happen is that if any one of these tasks is holding on to resource R, CSC will become equal to 10. If CSC is equal to 10 and T4 wants to access, assuming some other resource, which is not R, in this case we call it CR1, it will not be able to access it because it was not the task which set the current system ceiling, and its priority is not greater than the current system ceiling. So this is a new kind of an inversion which we have not seen before, which is exactly leading to the delay or the deferral, which essentially means that T4 can access this resource CR1, where I'm assuming CR1 is different from R. But, and let's further assume that the lowest priority process T2 is holding on to R. The sad part is that T4 will still be made to wait because, in a sense, T4 can execute. It can execute on the CPU as much as it wants. But pretty much to get hold of a resource, its priority needs to be higher than the current system ceiling, which it is not. So if you look at the working of PCP, let me now show you. So let us assume that process T2 gets access to a critical resource and the priority of T2 is 2. In this case, higher the number, greater the number, higher the priority. So the current system ceiling is actually set to 10 as per this diagram, all right? So which is fine. So which means that in a certain sense, T2 is holding on to a hot resource because it has a high ceiling, which has set the current system ceiling. So assume that after that, T3 starts to execute. So it can execute. So in this sense, unlike HLP, which would have also boosted the priority of T2, in this case, that's not happening. So if T3 wants, T3 will continue to execute because its priority is 5, right? So it can execute on the CPU, no problem. This is where there is a vital difference as compared to HLP because we don't have such inversions. But now let's see. Now assume that T3 tries to get access to the critical resource. Here there will be a problem because the resource is not preemptible. So T3 will wait on T2, and furthermore, the current system ceiling will still stay at 10. But the idea is the priority of T2 will increase from 2 to 5. As you can see, it was 2 here and now it's 5. The reason being that an inheritance has happened. So after that, T2 will let go of the resource, so its priority will default back to 2. The current system ceiling will still stay 10, but the resource will come to T3. And then its priority of T3 will be 5. And now assume there is T4, which wants to access resource CR1. So T4's priority is not great. It's less than 10, it's 8. So technically speaking, it has a high priority, but it will not be able to access it because this is less than the current system ceiling, right? So this is something new. This is something which is different. So the reflections will be that a task, when it is granted a resource, only the CSC changes, right? That's all that changes. The priority of the task per se does not change, right? This is a key difference as compared to HLP, for example. But the priority of a task will only change when the inheritance clause gets applied, right? So when we see that the inheritance clause is applied, which means a high priority task is waiting on a low priority task, that's when the priority of a task changes. So the analysis of PCP would be, so these are things that we will see in the current lecture as well as in the next lecture, with proofs of course, that we will prevent deadlocks, we will prevent chain blocking, unbounded priority inversion, and what used to be our biggest problem with HLP, which was inheritance related inversion, this will be limited. So this of course is something that we saw in the previous slides. So what we saw in the previous slides is basically that the inheritance, so what happens is that unlike HLP, we don't raise the priority to a very high value, to an unrealistic value. It is only raised on the basis of which tasks are actually waiting on a low priority task. So this reduces the effect. So here inheritance related inversion is more or less as bad as priority inheritance. And of course, we will see that deadlocks, chain blocking, and unbounded priority inversion, all three cannot happen. We'll prove a single theorem pretty much similar to what we had done in the case of HLP, which will tell us that all three are not possible, right? Right. So basically, in deadlock, we'll see that a cyclic wait is not possible. Here, we'll see that a task gets blocked once, and here again, we will see that there is priority. A task suffers priority only inversion only once. So that is enough to basically prove all of these. So there are different kinds of priority inversions in PCP. So one is of course a direct inversion, which means that a low priority task is holding on to the resource and a high priority task comes, and then we see that it needs to wait. The other is inheritance related inversion, where this low priority task is executing, of course, with the priorities of the high priority task, and then an intermediate priority task comes whose priority is greater than that of the low priority task, but it will not get access to the CPU because of an inheritance related inversion problem. Then, of course, we have avoidance related inversion. So, here again, the main problem is that if you would recall, the new kind of inversion has been introduced in PCP, where basically to get access to a resource and continue the execution, the priority of the task, if of course it has not set the current CSC, has to be greater than the CSC, not equal to, greater than the CSC. If that is not the case, as we saw for task T4, then of course what will happen is that this task will wait. It will not get access to the resource. There will be a delay or a deferral. And this is of course something new, a new kind of inversion that we have not seen before. So this is known as an avoidance related inversion, which happens because of the resource grant rule. So the direct inversion, as we have seen, just described, TL waiting on TH waiting on TL, high priority task waiting for a low priority task. Inheritance related inversion is basically when the priority of a low priority task is raised and then an intermediate priority task does not get access. This is inheritance related. All right, so basically, this is a classic diagram for inheritance related inversion. Avoidance related inversion is where a low priority task that is holding a resource, in a certain sense, the CSC is made equal to the resource being held, and then a high priority task comes in whose priority is, however, lower than the CSC, but it needs a resource that is currently free. So you can say currently free, not in use, same as free. It will undergo avoidance related inversion as per the resource grant rule on the lines of what we have been describing, which is something new in PCP. All right. So this is also called priority ceiling related or deadlock avoidance inversion, as we shall see, right, when we will look more into this kind of inversions. But different names, we will use avoidance related inversion, but different names mean the same thing. So avoidance related inversion can be shown here. The ceiling priority is set to 10. We have a high priority task with priority 8 does not get access. So now let's look at a key theorem. So the theorem is tasks are single blocking under PCP, which means that once a task acquires a resource, right? So when does it acquire a resource? So it acquires a resource when either its priority is greater than the current system ceiling, right? Or when it was the one to have set the system ceiling in the first place. But well, if it set the system ceiling, so let us just go back in time to the point where it actually set the system ceiling. So then what happened? So maybe it still had a resource, right? And then it acquired a new resource whose ceiling was higher. So that set the system ceiling. So that again doesn't count. We go back until we come at a point at which it did not have a resource. So if it did not have a resource, it could not have set the CSC. So at that point of time, this condition must have held true, that the priority of the task is greater than the current system ceiling. And the current system ceiling could have been also zero at that point, which means no resources have been taken, but that doesn't matter. The important point is that whenever a task acquired a resource for its first time, its priority must have been greater than the current system ceiling. Once it has acquired a resource, after that, the other condition of the resource grant rule kicks in, which is that since it has set the current ceiling, it will continue to acquire resources, right? So this is pretty much, if you think about it, this is pretty much the only time that the task will actually block, because it doesn't have a resource. It tries to acquire its first resource, and it will not be able to acquire it because maybe a low priority task is holding on to it. But once it has left, the next time if it has the highest priority among all tasks, it will get it, right? But the important point is that once it acquires a resource, it will continue to execute unless another task comes in, which is Tj, which is greater than the current system ceiling, right? Which means its priority is greater than the priority of Ti, but in that case, it's a high priority task, so we don't care about it anyway. In the sense, Tj blocking Ti will not be counted as a priority inversion. Okay, so which basically means that once a task acquires a resource, the first resource, it becomes the one to have set the ceiling. It will continue to acquire resources unless it is, of course, preempted by a much higher priority task. But again, when that finishes, so the control will anyway come back to Ti, and Ti would have been deemed to set the current system ceiling, right? So that is not important. But the point is that only the first time does Ti have a difficulty. After that, the only ones to actually preempt it are tasks with a much higher priority. That does not count as inversion. So what counts as inversion is the very first time. So given the fact that we have proven, so recall that even for HLP we had proven something similar using the logic was also similar, but the important point is that tasks are single blocking. So a corollary would be that under PCP, a task can undergo at most one priority inversion, which is at the time of acquiring the first resource, not anymore, right? So, and also, why will it undergo? Because it just arrives, it tries to take a resource. At that point of time, the resource is with a low priority process. That is when you need to wait. But once the low priority process has released, so then TH will not undergo an inversion. It may still not get the resource because another high priority task would have arrived whose priority is greater than TH. But mind you, there will be no inversion. So why is PCP deadlock free? So deadlocks will occur when different tasks hold parts of each other's required resources. So the classic example of task 1 trying to lock R1 and then trying to lock R2, and task T2 trying to lock R2 first and then R1. But what will happen is that under PCP, when a task holds some resource, right? So let us say it holds resource R1 and T2 is interested again in that same resource, right? So let's say, why are you having a deadlock? Because T1 and T2 are interested in both the resources R1 and R2. So you can happily say that the ceiling of T1 is greater than equal to the priority of T1. It is also greater than equal to the priority of T2. And something similar holds for the ceiling of T2 and something similar holds for the CSC, right? Which basically means that priority of T1 is not greater than the CSC, priority of T2 is not greater than the CSC, right? So I can write it like this: priority of T1 is not greater than the CSC and priority of T2 is not greater than the CSC, when of course only both of them are involved, which means that if one of the tasks acquires any one, either R1 or T1 acquires R1 or T2 acquires R2, by the resource grant rule, the other task cannot displace T1, right? So, which means that no other task can hold a resource that it may need. So, given the fact that once T1 has acquired R1, R2 can simply not go to T2, a deadlock is not possible with T1 being the first, and the same logic holds when T2 accesses R2 first. Then also a deadlock is not possible because of the fact that once R2 is acquired, the rest of the resources also T2 will acquire. All right. So that is the key point, that when two tasks are interested in the same set of resources, these equations will come into play, which basically means that the resource grant rule will not allow one task to preempt the other. So that is the insight. So the insight is that preemption in this case is not possible. So basically, if T1 is holding a resource, then no task can, no basically conflicting task, and in this case T2 is a conflicting task, right? So let us call it a conflicting task where they are pretty much interested in similar set of resources. So no other conflicting task can hold a resource that it may possibly need. So how is unbounded priority inversion avoided? Well, unbounded priority inversion is basically when it is waiting for a low priority task to release the resources. In the meanwhile, multiple intermediate priority tasks preempt the low priority task. So in this case, what will happen is that the high priority task which is waiting will give its priority to the low priority task. So it will inherit the priority, and this will stop intermediate tasks from actually running because they will not be able to preempt it on the basis of priority. As a result, unbounded priority inversion will not happen. How is chain blocking avoided? So basically, given the fact that resource sharing under PCP is single blocking, chain blocking will be avoided like this. Tasks are single blocking, so basically they block only once, they don't block multiple times. So that is why, because they don't block multiple times, we will not have chain blocking, by definition. So this finishes this lecture on the priority ceiling protocol, its important properties and its proofs. In the next lecture, we will discuss more examples and we will look more into the priority ceiling protocol.